Welcome everyone. Today we are very happy to have Mikhail Solon from UCLA, who is going to tell us about quantum field theory tools for gravitational waves.
Cool, thanks. Yeah, thanks for having me. It's been nice to be here, although as I was telling Sav, I can't help feel like I'm still a student here, even though that was a long time ago. Yeah, so I'm going to be talking about applying the tool of quantum field theory for gravitational wave science. This has been a research direction that I've been doing with many people. Too many to mention, but I'm happy to point you to papers later on. So the main idea is basically to compute things that would be needed to make sense of data from gravitational wave observatories, such as the fluxes of energy and angular momenta, basically solving the two-body problem by thinking about by using tools in quantum field theory, such as scattering amplitudes and effective field theory. Okay. Of course, this is motivated by this wonderful experimental program that we have now since 2015, when LIGO detected the first, or had the first detection of gravitational waves, rather, up to today, where we now have this network of detectors composed of LIGO, Virgo, and Cagra, and this rich experimental program will hopefully continue on with detectors such as LISA, the Einstein telescope, and Cosmic Explorer, which will require higher precision in so-called waveforms, or basically the what we observe from these binary end spirals. Okay. Now, with that higher precision, there's some challenges to the normal way of calculating these things in general relativity, the post-Newtonian expansion, for example, et cetera, where those methods may not scale to the precision that's required. And that's because this problem, the two-body problem in general relativity, is quite hard. It has multiple scales, even for just two black holes in spiraling about each other. And those multiple scales are coupled nonlinearly. Okay? So that's the hallmark of Einstein's equation, that it's highly nonlinear. But exactly these two things, the fact that there's multiple scales and the fact that they're coupled nonlinearly, are the same kind of difficulties that led to breakthroughs in particle theory over several decades. Those hallmarks are also in QCD. So when we think about bound states in QCD, or even just scattering in QCD, we encounter multiple scales that are highly nonlinear, and those have led us to tools such as effective field theory and scattering amplitudes. So these are powerful mathematical tools based on physics, all the way down to really core technologies, such as just integrating things. And so we've developed this large machinery for QCD, and the idea is to basically take this and apply it to gravitational waves. Okay. Now, the hope, of course, is that not only do we get to use our favorite tool, quantum field theory, to compute something that's very relevant to this active experimental program, the hope is that we will also learn stuff about quantum field theory. We learn a lot about quantum field theory when we apply it to a specific scenario, here, gravitational waves. And as I will show you, this scenario has features that make it special. In particular, it's classical, which is really the physics of large charges. And we're interested in, maybe we'll learn new properties of amplitudes in that regime. Okay. So just to lay out clearly the goals of this program so far, the goal is to basically compute precise waveforms. And this includes higher order corrections to the two-body problem, corrections from the spin of the black holes, corrections from the finite sizes of the neutron star, from the radiation emitted, and so on and so forth. And these calculations will be done using quantum field theory tools and will be mostly analytic. And the goal is not to supplant numerical relativity. That is not a good goal. but rather to complement it. So depending on certain properties of the binary inspiral, such as eccentricity or the periastron and so on, there are certain regimes where numerical relativity is effective. There are some regimes currently where it's not effective, possible, but very costly, and so on and so forth. So these analytic waveforms are meant to complement those. And in hand with this, of course, is to develop the tools. So some of the tools that we know and love when we apply to QCD are directly applied onto it. As I'll show you or discuss later on, the bound states in quantum mechanics, such as QQ bar, for example, have actually a lot in common with bound states in the astrophysical setting. So some of those tools directly are applicable, but still there are, as I said, it's a different regime. So there is a chance here to develop new ideas. And then finally, just to go back to this point, is that we want to also explore QFT structures. Okay, so one thing that's important when, in my view, when we say that we have a different way of calculating something, is not just it's a different way, that it actually enables to compute new things. And that's been the case here. We've actually have new calculations or new results that were previously unknown in GR, okay, through this method. And this was welcomed, for example, before these results came out in a 2017 paper by Damour. He was already asking if it was possible to compute the 2-to-2 scattering in gravity of two scalar fields, which would inform, for example, higher order corrections in the two-body correction. And then when the results came out in some papers in 2019 and also 2022, people who are members of the LIGO-Virgo-Cagra collaboration, led by Alessandro Bonanno, actually explored the solutions that we got using quantum field theory and looked at how well they did. So what did they do? Well, they basically plotted it. So for example, one of the plots they made was a plot with binding energy in units of the mass, total mass of the bound state, as a function of orbits to merger. Okay, so the solution from numerical relativity looks something like this. There's another line which is due to EOB. EOB is this effective one-body model, which is one of the phenomenological models that they use to produce waveforms. And it's essentially on top of this line. So I won't draw it again, but these two are basically the gold standard results for producing waveforms. And the results from QFT, something like this. So we won't really pay attention to the y-axis numbers. I won't write them out. They go from 0 to minus 0.12 negative binding energy for a bound orbit. For orbit submerger, it's nice to keep track of it a bit, just so you can see how well this thing does. The tree level calculation basically ponks out here at about 10 orbits to merger. So there's still 10 orbits left in this binary inspiral before they merge. That's how well this order G calculation works. This is a tree level calculation where you scatter two scalar fields and exchange a graviton. At order G squared, it improves, but still it starts to fail at 5. And order G cubed improves a little bit more on top of that, and it starts to fail at 3. And then order G fourth, which is the state of the art that we've computed so far, is starts to conk out at like so I guess 2 here.
So binding energy increases as you go down. Is the
Binding energy is negative. It starts from 0 to minus 0.12. So you're losing energy as you orbit close to merger because you're releasing gravitons. Okay. So let me just relabel these things. This is G squared, a one loop calculation, such as from a graph like this. This is G cubed, to-do calculation, such as from a graph like this. I'll come back to this graph later on. It has some interesting properties. For the experts in the audience, you might recognize it as some contribution to the Reggie trajectory. And then at G4th, it improves, but still not as good as EOB or numerical relativity. So at this point, let me just draw a G4th graph. My vertical lines are always black holes. The exchange squiggly lines are gravitons. Okay. So which improves, works good up to, let's say, 2 orbits to merger, but that is not good enough. So these results are new in the sense that these are functions that were computed before, and I'll show you what they overlap with in terms of previous literature in the general relativity community. But yeah, the precision needs to be improved. But the main message here was that, you know, this wasn't in vacuum, that we were actually able to communicate the results to people who are developing waveforms for these experiments. There's a similar plot. So this is for binding energy of a bound state that's orbiting towards merger. They also looked at, I'll just be brief here, the scattering angle as a function of impact parameter for a unbound trajectory. So here you'll imagine you have, this is, let's say, your impact parameter, and it scatters like that. And basically this thing here is your scattering angle. And again, they have simulations of this using numerical relativity, and they plotted 3-level, on-loop, 2-loop, 3-loop results, just to see that it actually makes sense. Okay, so these guys are definitely interested. In fact, one of the things that they did was to go back to this binding energy case, and instead of treat these predictions from QFT as separate, they actually used that information and fed it into EOB. So EOB is this big function that they parameterize with some principles in it, such as they should get the right limit when they go to the Schwarzschild limit. It has in it known results from the PN and so on and so forth, but it's like a big function that can absorb information from many inputs, even numerical relativity. So what they did instead was incorporate this G4th result from QFT into EOB, and they also found agreement to the point that it actually was pretty close. Okay, but you know how that is done. There's some gauge dependencies in there, and so on and so forth. So this really has an error bar. So I think it's not that I'm making the point that we've reached the state of the art and they should be using our results to produce waveforms, but rather just to highlight that they really are interested. They're looking at even the effects of these new functions into their models. So just to get everyone on the same page, what I'm talking about here when I say waveforms are, like, see these plots of strain as a function of time. And there's this early part where the two black holes are far from each other and they're inspiring slowly. And this is where our calculations are working. Okay, that's when they're still far apart. There's still a long way to go before merger. But once you get to merger, this part, then this is where you would use numerical relativity. So analytic methods here. And here, when they've merged, there's a ring down phase where you describe basically modes ringing on top of a black hole solution. Ring down. So the things that we've been computing, where these two black holes modeled by these scalar fields exchanging gravitons, they're far apart, and that corresponds to this region here. Okay.
So the fact that we're treating them as scalar fields means they have a small angular momentum. Like, why don't we model?
In principle, you mean have them spin?
Yeah.
Yeah. So in this case, I'm talking about black holes that would correspond to Schwarzschild, no spin. We could replace the scalar fields with some particle and some
then what's the
representation.
state of the art?
What's the state of the art? It's G cubed.
G cubed.
Yeah, two loop is the state of the art. And also, when you replace a particle with spin, you're also expanding in spin.
Yeah.
So it's only G cubed, I think S squared.
Why are you expanding? And
So for example, the curve solution is all orders in spin.
Yeah.
So I could hand you the geodesics to all orders in the spin, but when we compute perturbatively, the spin parameter is actually expanded. It's not an all orders resultant spin.
It's a technical difficulty, or there is a fundamental reason why one cannot treat even without expanding it.
Yeah, so there's at leading order in G, there's actually a nice trick. This goes back to a paper by Utin and Nima, and maybe you, right? Yeah. Where there's a nice expression for the 3-point function, which is an exponential in spin. And if you stick that in, it gives you curve back. But sticking it to higher orders, namely, you need to know the Compton to all orders in spin. Nobody's figured out the Compton to all orders in spin. Order by order, we can compute the Compton up to S to the 4th. But there's some issues at higher orders. But so, yeah, I'll talk about spin in a little bit more, but mostly I'll focus on the scalar case. There is of course angular momentum between the two.
yeah, no, but I meant the.
Yeah. Any other questions? Okay, so what do we mean again here when we said new results? If we look at powers of G, let's say this is the exponent of G, so 1, 2, 3, 4, 5, 6, 7, and this is the exponent of V. It would be 0. I'm only focusing on I'll be focusing on the even powers of B. So the time symmetric solution, which corresponds to conservative dynamics. So if you notice here, all the graphs I'm talking about are 2-to-2 scattering graphs, which are the exclusive process, which of course is physically non-sensible unless you can actually isolate what you want. These are infrared divergent.
V is the velocity.
V is the velocity, the relative velocity between the two objects. So this box here, was solved by Newton in the 1600s. That's Newton's law. So these are basically conservative corrections to Newton's law. And here is the first post-Newtonian corrections. I remember when I was a grad student here, there used to be a guy who goes to the seminars and shouts post-Newtonian correction from the back.
Yeah. An old guy.
Yes.
To all colloquiums. All colloquiums.
Yeah, I was a little worried about that coming.
Yeah. He's there.
More than average. Okay, and then
He's still
so the post-Newtonian calculations go along these diagonals. So this is the second post-Newtonian. The first post-Newtonian was of course calculated by Einstein, Infeld, and Hoffman in the 1930s. So 1600 to 1930s, pretty big time separation there. And then people have marched along 3. The state of the art is 4, which was calculated by Thibaut Damour and friends sometimes in 2010 or something like this.
What's observable in our solar system? Just 2? Like if you just look at like perihelion shifts and things of that nature, can you get to 2?
Oh, yeah, that's a good question. I don't know. Does anyone know?
No, I'm not sure what it would be.
I think probably 1 for sure, right?
No, one of course. No, I think I remember that it's 2.
Well, for
I think it's 2.
Okay, so the state of the art is 4. When it comes to 5, it's almost known. It's known up to 2 free parameters. And so this is the 5th post-Newtonian result. It's known up to 2 free parameters, which have to do with memory contributions, which people are still sorting out. And then when I mentioned earlier that there's going to be these experiments, Einstein telescope and Cosmic Explorer, the ballpark is that the sensitivity will increase by at least 2 orders of magnitude, and that lands you somewhere here, about 6 p.m. Okay. But in terms of what we've been computing, because we start from scattering amplitudes, we want to actually use relativity to compute these corrections, and what we've computed are all orders and velocity corrections. Okay, so the post-Newtonian expansion is an expansion in small g and then slow velocity, whereas when we say we're computing in quantum field theory, just like in QED, it's fixed order and coupling, but all orders and velocity. So then all of these would be known, and as you can see here, for example, the 2-loop result G cubed would have all this whole column of new results that were previously unknown. Where they overlap up to this 4, then those are checks. The checks are straightforward but somewhat tricky, just because typically when you open these results in GR, they're in all sorts of other gauges, and you either have to compare by calculating physical observables or finding the gauge transformation. But so interestingly, there are these new pieces, and in fact, when we first put it out, Thibault was one of the first people who immediately checked this and then declared that we were wrong in the V to the 8 piece. And for a while, he was very convinced we were wrong. He even wrote a paper saying what the number should be and so on and so forth. So there's been an interesting discussion, the dialogue with the particle physics, between the particle physics community and the people who are experts in this field, the GR people. Okay.
So this 2 free parameter is now computed?
Not yet.
No, but you said the EFT, using EFT, one can find 5 PN.
Just this part of 5 PN.
Which does not depend on the 2 free
Which
parameters.
doesn't depend on the 2 free parameters. Correct. Yeah, the 2 free parameters have to do with these memory contributions, which start at G4th or G50. So G4th is also completely known, although that was also part of some debate, namely that in the GR literature, again, when we opened it up, there were some discrepancies between our results and theirs because of this memory effect, which turns out to rely on a very sensitive cancellation. But, okay, so that's the summary of or at least one summary of the results so far. But as you may have thought, there's some question marks here. So first of all, how do we actually, maybe the easiest question mark is, how do we actually relate quantum to classical? Of course, I might say that's easy because you just put in H bar. I like to use H bar equals 1, but you can always undo it, put H bar back, compute, and expand. But this has to be done in a scalable way. Okay. And if you know, in particle theory, we haven't even really done many calculations at 4 loops. So how the heck can we even do any of these calculations that would really matter for the gravitational wave science program if that were the strategy? So this is the question mark. And the other question mark here is something that I haven't mentioned yet, but let me mention it now, which is when we compute from scattering amplitudes these quantities. Remember, this is a table of the corrections to Newton's law, which is a potential. We are relating a quantity that is defined for a scattering trajectory. So scattering amplitudes have been built in asymptotically free initial states, they interact asymptotically free final states. But those are not the same states that are the bound states. And so how do you relate these unbound orbits to bound orbits? Okay. And the upshot is that up to lowest order G cubed, the naive thing that you could do, which is to say, well, once I have the Hamiltonian, it doesn't actually matter what the orbit is. If I hand you the Hamiltonian, you can solve it for a bound or an unbound, it's universal. So then the trick might be, okay, let's just compute a potential using this by defining a potential and matching it with scattering amplitude. And that works up to G cubed. So up to G cubed is just a universal Hamiltonian. But it turns out that at G fourth, this Hamiltonian is no longer universal. And the reason goes back to graphs like this. So before G fourth, all the graviton exchanges are actually due to these gravitons called potential gravitons, which are instantaneous exchanges. They generate potentials, their energy components are much, much smaller than their spatial components. So all of these actually happen at a single time. But when you have a graph like this, there's actually a contribution coming from radiation modes, which has to do with this thing called a tail effect. And because of those radiation modes, you're now actually sensitive to the propagation of your state moving forward. So it knows about when it was released here, and it knows about when it was reabsorbed here. And if you define a Hamiltonian in terms of a result like that, you end up integrating over time. And when you integrate over time, this means that you actually know about their trajectory. So at G4, the Hamiltonian is no longer universal. There's a term that's non-local in time and depends on the trajectory. And that's an issue, because this whole program relies on extracting classical physics from scattering amplitudes.
Sorry, can you elaborate on that? So the Feynman diagram, you would integrate over the position of the exchange graviton, including the time. So in any of the, say in the two-loop diagram also. So what is special about the two-loop versus three-loop? I didn't understand that.
So in the two-loop or any loop before three-loop, all these gravitons are actually instantaneous. So their energy components, Q0 squared, their propagators look like this. And these ones are smaller than this. So you get to expand them upstairs. If they don't have the time component in the denominator, they're just instantaneous exchanges.
But some component of the momentum is an integration variable. So how could it be smaller? There are regions of the integration where it would not be smaller, right?
These are, so we're only interested in the region where it's smaller, and that defines for your potential. In the region where it's not smaller, it's order this, then it's actually an on-shell mode, which is a radiation. That's exactly the problem. So here, there are actually contributions, exactly. You cannot just expand this in the numerator because you find that, well, there's a region in which this is of order that, which is a radiation mode. So if I were to just do this loop, I could just take all of these to be potential modes, which have this property. But if you do that here, then you miss out the contribution to the radiation modes, where some gravitons here have the full propagator.
And sorry, and the conclusion about the d to the fourth term is that was what, that does not exist a local Hamiltonian?
Yes. It becomes local when you integrate, when you do the time integration. So there's an integration over time, and if you give me a trajectory, then it becomes local. Any Hamiltonian that we compute out of this process is local. But that local result actually already did for you the time integration.
So at some sufficiently high order in this expansion, there does not exist a Hamiltonian.
That's local in time.
That's local in time
Yeah.
for computing both bound states and scattering. That's what you're telling me.
Yes. If you do that time integral, then it becomes local in time. But that time integral now depends on the trajectory that you integrated over.
But if I was just a very naive person doing the post-Newtonian expansion and it was very powerful, wouldn't I always
So they also,
eventually find a local Hamiltonian, a local potential?
yeah, so their Hamiltonians have integrations over time. So it only becomes local because they assume a particular orbit, let's say, but let's say circular orbit or elliptic orbit. But before that, they also have an integration over time variable. So maybe another way of saying this, well, I don't know if it's better or not, but these contain logs that you have to integrate over. Okay, so what is the basic setup? So let me in the remainder of the talk, let me try to discuss these 2 points. First, what is the basic setup? So the basic setup is that we have Einstein Hilbert. So let me just write the action dx root G minus R 16 pi G plus, as I said, I'll stick to scalar fields here. We can use other representations, but other spin particles, but let me just stick to scalar fields here. So I have two scalar fields coupled through gravity. That's the basic setup. And if we were to compute, let's say, the tree level graph plus the one loop graph, and let me try to do it just the most obvious way, which is to put H bars back in, calculate, and then expand the H bar. And just for the sake of illustration, as I said, we do this to all orders in V, but just to illustrate it here, let me just look at the static result. So what you'll find is that after you compute this, and then you have a function of Q, which is the momentum transfer here, you go to real space via Fourier transform and you pick up a potential. So this potential is given by Newton's potential plus the correction, the first, let's say, M1 and M2 are the masses, and this is the first correction. And just to illustrate, let me keep the H bar. So if you actually do this and keep the next order, you find 41 over 10 pi G squared M1 M2 H bar over R cubed. Okay. So these quantum corrections to the potential are computable. They're quantum corrections in the long distance. So there's nothing funny about these quantum gravity potentials. Of course, this is not what we mean when we say we want to solve quantum gravity. But nonetheless, this is a quantum mechanical effect in gravity. Unfortunately, if you plug in solar masses here, this turns out to be suppressed by 10 to the basically 72 orders of magnitude, or 76 orders of magnitude, something like that. So unfortunately, these are not testable in these experiments. The same fate is for the higher dimensional operators to GR as well, like R cubed, higher order Riemann terms in GR, those will also be suppressed. Okay.
There is no classical contribution that falls off, also like on the R cube? Or
There is at next order.
what comes?
So this would be 1 on R cubed.
So there is no separation, no way one can separate this. Is there a way to separate the quantum?
Yeah, so that's what I'm gonna get at. How to, so this is not how I want to do the calculation, because otherwise I have to put H bars in and actually do the quantum loops, which are difficult. But just to illustrate, this is what we expect. It's some series in G over R, and then when you put H bars in, then you have to mix it by dimensions. There's an extra R cubed. And then the second point I wanted to make was just that, unfortunately, this is hopelessly small.
What is, just for comparison of numbers, what is the difference between like the order 4 and first order term that you're talking about numerically? I mean, you said that this one is down by some huge numbers of order of magnitude, but you're also going to very high order in some other parameters eventually. So I just want to understand that as well.
Yeah, so this is down because of a factor of, actually, I'll get to that in a second. So maybe come back to me if I don't answer the question. Okay, but the other key thing that I want to point out here is that the first way that we would model these classical systems as particle theorists actually works. So, we can compute potentials and so on. In fact, just with this calculation, if we were powerful enough, we could compute these higher order calculation or corrections to two-body problem. We could include corrections from angular momentum and energy loss. We could assume not scalar fields, but other spin particles and describe spinning black holes. Or we could also include operators like in this action, we could add operators like phi squared, Riemann squared, or higher dimensional operators that would model for us tidal coefficients. Okay, so with log numbers here. You could also use the same techniques to model n-body systems. So for example, there's some interest in 3-body systems in the hierarchical limit. And finally, you could also look at higher order corrections to Einstein gravity. So this, for example, would be an R cubed corrections. So, but just this basic setup, you could investigate a lot of things. Okay, so scattering amplitudes in this way definitely encode classical physics. Okay, now, as I said earlier, the bound systems, the classical bound systems that we're talking about actually have a lot in common with quantum bound systems like the hydrogen atom or QQ bar. In fact, that was the key insight of the work that's been called NRGR by Goldberger and Rothstein, was to take technology from QQ bar and hydrogen atom, namely NRQED and HQED, to binary systems. And for example, if we look at these amplitudes that describe 2-to-2 scattering, we find the same scale. So there's a hard scale, soft scale, potential mode that I've been talking about, and a radiation mode. And in terms of energy and three momenta, these scale as mass of the black holes or hard, which is why we don't like hard, that's quantum. If you exchange momenta that's order the mass of the black hole, then you have to pair produce or eight black holes. For soft, we have mv over j. And inside soft, you can actually divide this phase space up even more into what's called potential and radiation, and that would be mv squared j and mvj. So this is the mode that's responsible for these instantaneous potentials, where the energy component is smaller than the momentum component. And then there's the radiation mode, which is the case where the energy component and momentum component are the same order. So notice here I've done something that we don't normally do for bound states of hydrogen and so on, which is I've written out the J. Because for those kinds of bound states, J is just order H bar, which we set to 1. So when we look at, say, a QQ bar bound state in HQT, H bar is 1, and then we just expand in these small parameters. So here comes the first difference of classical and bound states. So they're similar in that they have the same modes, but they're different in that quantum bound states have H bar of order 1, while classical bound states have angular momentum R cross P, which is much, much greater than H bar. Okay, so if we want to take the classical limit of these results, we parameterize with H bar set to 1, we parameterize this in terms of this large angular momentum and send that to infinity before doing any of the integrations. And then the second thing, which connects with the suppression of that term, is that a solar mass squared, or not squared, solar mass over m Planck is actually 10 to the 38. So solar mass over m Planck means that these guys are enhanced by 10 to the 38 squared compared to this one. So this is the suppression. Just if you plug in a solar mass, that's how large this charge is. So classical physics is describable from the scattering amplitudes or this QFD, but you have to take the limit of large charges. In contrast, square root of alpha is just 0.1. Okay, so we're using
to the power of 57.
Sorry,
Is that 57 or 38?
38.
Solar mass over
Solar mass over m Planck. Whereas if we talk about, electrons, which have unit charge as fundamental particles, then this expansion, the analog of this, is 0.1. So quantum particles have small charges, and that's why they're in a different regime. So just think about this as we compute the amplitudes, but we have a double expansion. One is in powers of m over m Planck. Let me just use G. So G m q to the A times Q over M, the B. So if each amplitude is expanded in this series, of course, there's a fixed order of G, since we're already doing perturbation theory. The higher orders of Q are just quantum corrections. And really at each order in G, there's a right power of Q. Q is the momentum transfer. Yeah, in this process. Amanda Sam T, square root of T, or minus T. And so for for general relativity, or for this application of general relativity, what we're interested in is reading off these terms in an amplitude and throwing away these quantum corrections. Whereas here, it's a completely different regime, where it's actually the classical results that are small. So if you're a quantum physicist doing QED, the classical pieces that are actually the small ones, because this GMQ is a small number. Okay, so that rule, these rules, along with this power counting, is basically implemented at the level of the integrand. Now we have an EFT or a way to power count the terms that we want. And you can recompute this and never have to encounter this term here. You never have to do this loop. You already know it's suppressed just by power counting. So you just implement large J and know that in the large mass limit, you're after a particular power of Q. So essentially you're going to expand in small q. Okay. You can also transcribe these rules into rules for Feynman graphs. There are obvious ones. For example, any kind of Feynman graphs where the number of black holes isn't conserved, obviously pair created or annihilated black holes, that's not possible. But then there's other more subtle rules that essentially boil down to careful application of these power counting. Okay. So now that we know how to extract classical physics, what is the roadmap for getting the Hamiltonian?
Sorry, the large J doesn't compete with the perturbative expansion.
It doesn't compete with a perturbative expansion. So
How do I see that? Like the
So first of all-
order G doesn't come down and can compete with the lower orders because of the huge J.
So I'll work at fixed order in G, so I'll compute in G, and then the large J is actually just a small q. So at every fixed order in G, I'll just expand in Mandelstam T. And that's the large J is small q. So the angle, so J is proportional to R. R is the Fourier conjugate variable to Q in momentum space. So large R is small q. P is fixed. Could be 1. Okay, so what is the roadmap? The roadmap is we compute essentially compute scattering amplitudes. For example, you could do it by using tools of unitarity to sew together tree-level amplitude and so on. We then extract at the earliest level, even in the construction of the integrand, the classical piece. Then we use integration tools as used in high order evaluations in QED and QCD, namely integration by part systems and so on and so forth, to get an amplitude out. And then once we have an amplitude, I'll describe to you in a second what we do to get a Hamiltonian. The construction of the amplitude, of course, you can do just using Feynman diagrams. But of course, at higher orders, it's nice to use more sophisticated techniques from amplitudes. For example, we use what's known as the double copy, which is just we compute tree-level Yang-Mills amplitudes. We square them. That gives you tree-level gravity amplitudes with extra degrees of freedom, which you can project out. And then you can use this in unitarity to sew them together and get an amplitude. Once you have this amplitude, then you use the EFT power counting rules to read off the classical piece. You integrate over the remaining integrals, and you have the final amplitude.
The double copy is not known to be true to all orders, is it?
It's not. So at the orders that we worked at, it works. We're confident it works. There are some orders where you actually have to correct it. We're not at those orders yet, so we're not worried. But yeah, the double copy is really nice, but it's also nice that we could just use old-fashioned Feynman diagrams, because there are actually a lot of systems where we're not necessarily interested in high orders, but just the physics of it, and you can explore that using good old Feynman diagrams without double copy and all that stuff. Okay, so I don't really there's one slide here on integration. I'm going to skip it on how the integration tools. How we've ported the integration tools from QCD and QED, but let me at least say some sentences about that. The basic strategy for doing this now is to essentially use integration by parts to solve the differential equations in velocity. So each of these integrals are a series in velocity because it's, as I showed you in the chart. What you can do is you can solve for the solution to this integral at the b to the 0 as a boundary condition, and then apply differential equations to solve to all orders in b. So that's how we use integration methods. There's also some interesting comments about the boundary value being an integral over multiple complex values. So in doing this project, I had to learn the hard way that if you integrate over a function of multiple complex values, it's not anymore a sum of residues, but you have to actually weight those residues. I don't know if you guys knew this before, but I certainly didn't. I just used Cauchy sequentially, but Cauchy sequentially won't work. Actually, you have to weight these residues in a special way. I thought it was quite interesting. Okay, so let me write out what the amplitudes look like a little bit. So, how am I doing on time, by the way? 10 minutes, is that?
15 minutes.
15
started 5 minutes.
Cool. So the free level amplitude, I'm going to use squiggles here. I'm not going to write out all the 16 pi's and so on, but obviously there's a g. The q dependence is 1 on q squared from the pole. And then this is just a rational function of sigma, which I will, or Mandelstam S. So it's a rational function of Mandelstam S. And that rational function of Mandelstam S, I'm labeling probe because it turns out that at order g, all you're really sensitive to is a probe particle in a Schwarzschild background. Okay. At second order, this is g squared, and the momentum transfer dependence is now q. So that this one Fourier transform to 1 on r squared, this one, sorry, 1 on r, this is 1 on r squared. And again, interestingly, this is completely fixed by a probe calculation. So it's a rational function of Mandelstam S. There are no logs at this level, which in contrast to a quantum calculation at one loop, you would already get logs. So this is one indication that these classical calculations are simpler. At third order or 2 loop, you get g cubed log q. So this log q will Fourier transform to 1 on r cubed. And you get another probe piece, which is a rational function of Mandelstam S. Now you have a log. And also a rational function, another rational function, let me just call it S, which are down by this parameter nu. This parameter nu is m1 times m2 over m1 plus m2 squared. So it's the reduced mass divided by the total mass. And so in the Schwarzschild limit, or when m1 is much smaller than m2, you all just get these probe amplitudes. Okay.
How should I think about the scale dependence of this log? Usually in effective field theory, I can adjust my cutoffs to make logs small or resum them. What are we doing here with these logs?
Yeah, so these logs, this log is a function, the dependence inside is like p squared over, it doesn't actually come from, it doesn't have a mu dependence as we computed it. So just to be complete, it should be something like,
Well, like for instance, in the log q, what's the cutoff on the what's the dimensionless variable in the log?
so if there were a dimensionless variable here, when you Fourier transform that, you just get a delta r, which is a short distance effect, which we've thrown out anyway. So if you Fourier transform log q, you get 1 on r cubed. If you have the whatever mu not there, then it doesn't depend on q. And so the Fourier transform will be delta r, which we're not interested in. We have no business talking about the contact interaction between these two black holes. So that we're not interested in. This is dimensionless inside. I didn't write it out. It's just the masses.
But there's no renormalization group on that log.
There's no renormalization group of that log, but you could. In fact, these logs, this is a double log, log times log.
Yeah.
This log actually comes from this ladder diagram. So these ladder diagrams resum to the Reggie trajectory, and in this order, it's a double log. Now that double log is usually log of s over t squared. But because of the way we're counting classical pieces, there's only the cross term that's classical. The other pieces are quantum. You could resum it, but if you resum it, you're basically like resumming a tower and then you only cross the classical piece once, so you don't necessarily care. There are some instances where the renormalization group actually resums interesting classical pieces, but not in this case. So here that it would be all quantum. Okay, so for G4th, so here we meet transcendentality 1 function. For G4th, let me just be really quick here. This is fourth, the Q dependence now is Q, which would Fourier transform to 1 R to the fourth. Still have the probe piece. And then you have the piece that's suppressed by this mass ratio, which is, by the way, a very interesting observation, which I'll come back to in a second. And in here, there is a tail piece, which comes with the log. And then an elliptic piece. So just to note that at this order in loops, we find elliptic functions. And then a piece of Mandelstam S, which have transcendentality 2, weight 2, such as dialogues and log settings and so on. So this is the kind of amplitudes that we need. So interestingly, we have elliptic functions at 3 loop, and there's this tail piece that's a log, which we had to renormalize. So this is where actually the radiation contribution comes from. If you delete those radiation contributions, you'll end up having a 1 over epsilon IR because your theory is not complete. And then if you add them back, there's a 1 over epsilon UV that cancels that, and you pick up these log. Okay. Okay. So one thing that I mentioned up there that's interesting is the fact that these amplitudes at fixed order in G actually overlap with what's called the self-force expansion. So for example, the leading G goes as M1 squared, M2 squared. The one loop correction goes as G squared, M1 cubed, M2 squared plus M1 squared, M2 cubed. At 2 loop, this is G cubed. This is M1 fourth, M2 squared plus M1 cubed, M2 cubed plus the 1 goes to 2, and so on and so forth. So you see that this whole first row here is really the probe limit. So this is what's also called 0SF, where these amplitudes basically describe for you a probe particle in the Schwarzschild solution. And in terms of amplitudes, what you find is that these are given by graphs where there's any number of propagators on the heavy side. So this is a scalar field with mass m, this is a scalar field with mass small m, and we're expanding in small m over big M when we talk about self-force. Okay, but this whole tower here in the leading M1 goes to infinity limit is given by graphs where the heavy particle has any number of gravitons and the light particle only has no propagators. So if you resum this tower of amplitudes, what you find is what we call the Schwarzschild amplitude, which corresponds to an amplitude where you have a probe particle or a probe scalar field scattering against a Schwarzschild background. This piece here would be 1SF in the sense that it's down by 1 power of small m over big M. And those would correspond to graphs with 1 propagator now on the light particle. There's no calculation right now that has resummed that or knows how to understand that in quantum field theory, but in GR, they have solutions for this, and it would be interesting to, one thing we're doing is we're interested in investigating those solutions from the point of view of amplitudes. Okay. Okay, so maybe just in the last 5 minutes, let me just finish up and tell you what we do with the amplitudes in the end, how we compute a Hamiltonian. Okay, so to compute a Hamiltonian, we basically have a Lagrangian, which is just the kinetic term, which is sum over I phi dagger I dt minus root squared plus m squared. I, so we have two scalar fields, phi1 and phi2. And with this, we add a potential term, phi1 dagger phi1, phi2 dagger phi2. And this potential, we just write everything it can be, which is just sum over coefficients, Wilson coefficients, which end up being functions of velocity times and powers of g over r. So this is the most general potential that you can have for two-body dynamics. It's in a particular gauge. Potentials are not gauge independent. You can always redefine a coordinate. But it suffices. It's the simplest gauge, in fact. It's called the isotropic gauge. So once you have this basic theory, you compute in this theory.
So are the Cn of p squared observable then or not?
Cn of p squareds are going to be turned. So this is the potential. So if I Legendre transform from this, I can go to Hamiltonian. So these Cn's are terms in the Hamiltonian. These are not observable. They're gauge dependent. Okay, potentials are gauge dependent. What we can observe is if we compute like a scattering amplitude. Oh no, sorry, a scattering angle, let's say, just to be specific to this context where we actually, So I take this potential, I compute these graphs, which are just these bubbles. And these graphs are up to some order g and they're functions of c. But I also know the answer to this problem in gr. And so I just equate this to my amplitude in gr. And I solve for c's order by order in g. And that's how I get the Hamiltonian. Okay, so these are known, computed from first principles. These are parameterized in terms of Wilson coefficients. I do a matching calculation, determine the c's, and now I have the Hamiltonian. There's some interesting things to note about this calculation in that we computed the first few orders of this and noticed the pattern, computed it to even higher orders, and the pattern persisted and then eventually proved it, which is that this amplitude here, this amplitude in the EFT, is actually solvable using a classical mechanics problem. So you can actually show that this amplitude in the EFT is actually equal to the radial action. So the radial action that you would get from solving Hamilton-Jacobi is this amplitude, which is very interesting because when you solve Hamilton-Jacobi, there's a way in which you actually avoid doing the integrations and everything is algebraic. So it's like you can do these loops to all orders just from algebra. But yeah, so this happens to be the radial action, meaning if you took the derivative of the amplitude with respect to the impact parameter, then you get the scattering angle. There's another formulation of this where this amplitude is given by a local observable p squared. But in any case, in both of those stories, it's interesting that you can solve for this amplitude to all orders by solving a classical mechanics system. Okay, so I'm happy to end here. I don't think I can cover the next piece. So just to close. Yeah, so it's interesting that gravitational wave science has opened up this new direction in research in theoretical high energy physics, and I hope I've shown you that classical binary dynamics really has the hallmarks of an interesting problem in theoretical physics, namely that we can use the tools that we love in quantum field theory. It's tied to a very interesting and alive experimental program, and it teaches us about theory, about QFT. And what I've described here so far is just the basics. I didn't even get to touch spin or finite size effects how to model those and so on and so forth. But there's been a lot of work, both in terms of pushing the precision of these calculations, but also in terms of developing the tools and trying to understand the theoretical structures. Yeah.
Questions? Yeah, so one thing, maybe you could say a little bit more about how you get away with either, well, not considering, it seems, radiation effect. I mean, the even powers of V is what I'm referring to. I mean,
Yeah,
At
so.
E to the fifth, you'd have radiation effects
Yeah.
that wouldn't be described by a Hamiltonian, but
Yes.
are
A G
obviously
to the
very
fourth, yeah.
important to dynamics.
Yeah, so
So, yeah, how do
Let-
you
let me answer this
either
question.
treat those or get away with not treating them?
Yeah, good. So let me first answer this question with what was the motivation in ignoring them in the first place? Which was, as far as we understood, when we talked to people who were doing these waveforms and so on and so forth, that in computing a waveform, there were basically two ingredients. One was some kind of quantity that described the conservative dynamics, typically, let's say a Hamiltonian, or let's say a periastron advance, or something that is proxy for conservative dynamics, and then a flux. Flux meaning flux of energy loss or angular momentum loss. And it so happens because of the timescales that you could model the system as conservative for a certain number of orbits adiabatically, and then let's say every other 10 orbits or so, you subtract off the flux. Just from the timescales that it happens. So it's not a principal thing, but that's how we started this game. Let's say, okay, since you guys are separating it, let's compute it separately. And in fact, when we computed G cubed, and in this graph, we had that log. And this was the first indication that you can't separate things. I mean, of course, in QFT, we know we can't separate things because we need really to describe inclusive processes. Namely that, when we say it's 2 to 2, how do you know it's 2 to 2? There could be a graviton coming from these externals, coming along with these external states. There's always that cloud. But just concretely, in terms of a calculation, this was the first place where it was in our faces. People were not happy because when they took the high energy limit, namely S goes to infinity, this blows up, but there shouldn't be any mass singularities in GR. So they were wondering what happened. This led people to think that we were wrong and so on and so forth. But the calculation, at least for the conservative piece, was actually correct. In a later paper by Thibault, he looked at the scattering angle and used linear response to write the scattering angle as the conservative piece, plus the first order response to any kind of flux. So you take the derivative of the conservative piece with respect to some variable, let me just, for illustration, use energy, and you compute the energy flux. When you add these two up, the log is gone, which is the calculation that you should have done. It's an exclusive process, or inclusive process, which includes the radiation emitted. But as far as this goes, you can still separate the two. Okay. In particular, this is time reversal invariant. This is not. At higher orders, that's no longer true. So, like I said, at G4th, we actually had to include a graph like this, where there's actually a radiation contribution to this, but it gives you an even V effect. Because you can always emit a radiation and get it back. It's time reversal invariant. And so we had to include that. That was included. But any sort of loss, we still excluded, just by not accounting for gravitons in the final state. But you could, in principle, include amplitudes with gravitons in the final state to account for the radiation and energy losses.
I mean, is there a reason that you don't do that other than it would be?
It was this reason
to-
that, we were talking to these people said, we want this and this, and they were separate quantities, and that it seemed like a reasonable place to start. Coming from the point of view of how these quantum field theory calculations work, it's not actually reasonable to separate them. They're tied together, but that's how they make that's. But yeah, it's a very interesting question, and it becomes really, really, really important at higher orders, especially at G4, where now there's also this memory piece that I talked about, where people have mistakenly written down the answer for this because the radiation contributions are subtle, and there were some non-cancellations that they were finding. But yeah, so if you want to include radiation, then you would look at 2 to 3 processes and compute the angular momentum and energy losses from this, assuming some frame, of course, because it's, it's gauge dependent, so on and so forth. But as long as you fix the gauge, so for example, you could wonder if this was angular momentum, in which BMS frame did Balmor compute this in? Well, he fixed it, and he made sure that it was the same one as what was used in the scattering angle calculation. But as far as I know, the scattering angle is BMS invariant, for example.
I didn't understand this part about the I radial. Can you say it again?
Oh, it's so, the interesting thing about this is that, the amplitude in the first place is just some amplitude. What is it? You have to pass through a potential and then a Hamiltonian and then compute a scattering angle. So normally if you have this amplitude allows you to define this potential using this maximum. Potential allows you to define the Hamiltonian. Once I hand you the Hamiltonian, you could now set up the problem where you have a body here, and the scattering, and you solve for the scattering angle. The magic of it was that you can actually solve for this amplitude algebraically to all orders. It's mapped to a solution in classical mechanics, which is the radial action. And then B, you can sidestep all of this and just take dDB and put the pi. So that
is this problem in classical mechanics?
The problem in classical mechanics is actually just the problem that you wanted to solve in the first place. Like this thing, if you solve this, you would be solving for the momentum at some position r by Hamilton's equations. And it turns out that if you some function of this, which I'll write now, which is the momentum at position r minus the momentum at infinity over 2e or root p infinity squared plus m squared, this is the amplitude. So it was very funny. We computed the amplitude to high orders, plugged in the potential, plugged into H, solve Hamilton's equation, and then while we were solving Hamilton's equation, you write this out in Mathematica and you notice, wait, I'm where I started from. Like I'm actually, this amplitude is just popping out to me order by order from solving H. So in fact, there's a connection between the amplitude, and the connection is, I guess, in the following sense, maybe a little more obvious, which is that suppose I handed you scattering data, you could do an inverse problem to tell me the potential. And so if you applied an inverse problem, you can actually map M to V that in this other way. I mean, otherwise, you just be doing this order by order in loops and there'd be no relation, but it turns out to be a specific quantity in this classical mechanics problem. Or even more interestingly, if you shifted, if you redefine things a bit, this becomes the radial action, which is, in the action angle variable formulation of Hamilton Jacobi, it's what gives you all your observables as a potential.
That action angle means something is integrable.
Something is integrable. What?
Well,
like
usually,
you're saying that I can.
Usually, when you have action angle variables, you're dealing with an integrable system, where you have as many conserved quantities as independent variables.
Yes.
Is that the case?
Yes. Yes, I believe so.
Interesting.
So interestingly, one question that I would have is for Kerr, the action angle formulation involves the Carter constant. And I don't know, it's something that it's a question that I've had, like, what is the Carter constant? So these amplitudes are all functions of the constants of motion, which are angular momentum and energy. But when we include spin, the Carter constant is in no way obvious. So I'm wondering, I don't know if there's any insight on what the Carter constant might be for amplitudes. But what is even the Carter constant in GR? From the point of view of amplitudes. But yeah, so the Carter constant supposedly is another constant of motion when you have a spinning black hole. And yeah, I'm just wondering what it would be for amplitudes. But anyway, that's my question. Yeah.
In terms of actual calculations of loops, as you know, there are a bunch of these basis integrals that one uses in scattering amplitudes. Like, so when you're doing these calculations, like how much of, like, I presume the integration is quite complicated. How much of that amplitude technique you can translate into?
Yeah, they're absolutely crucial.
Yeah.
In fact, at this point, let's say you just wanted to crank out the next order in that chart, just stay with the pure scalar case, you just want higher orders and so on and so forth. I'd say that would be the bottleneck, is the integrations.
So can you like write it in terms of those basis integrals, you know, like sometimes like, well. Like
Yeah,
just
you
depends-
identify a set of masters, you try to reduce them in terms of those, you get some relations using integration by parts. So yeah, at two loop, we did them the old fashioned way, and it's completely doable the old fashioned way. Everything with Reskin and Schroeder if you want. Apart from the integration over multiple complex variables, but at three loop, we definitely, you know, it was a no-brainer for us to use the integration by part, otherwise it would just be untractable or hard to do.
Right, let's thank the speaker again.
So this integral, this loop integral never had any